And this is section 6.3 in your unit handout. And then we have one more lesson in this unit after this one, and we'll be doing that tomorrow. So we're looking at proving trigonometric identities, and we have actually proved a couple already. Way back in, I think, 6.1, I did a couple of proofs for you. And we're going to talk again about verifying an identity as opposed to proving it. So I have on the board here, and I didn't print this out. This is almost identical to that pink sheet you have. So if you have that pink sheet in front of you, which you should, the title of that pink sheet says something like "When Working with Trigonometric Identities." And when working with trigonometric identities, all of these items were recommended to you except for one. And it's this one. So this is what's new. Because, and we'll go over this formally in the lesson, when you are trying to prove an identity, you're trying to show that the left side and the right side happen to be equal to each other. I can't remember exactly what it was, but there was an identity when we first learned about identities that was something like x plus 4 quantity squared plus 62 is equal to x squared plus 8x plus 78, I think. I'm probably wrong on the numbers. And what we did was we put in different values of x on the left-hand side, and we discovered that when you put those same values of x in on the right-hand side, you got the exact same answer. And somebody, I forget who, somebody had pointed out, well, yeah, because if you take x plus 4 squared, and you expand out x plus 4 quantity squared, you get x squared plus 4x plus 4x plus 16 plus 62. And if you simplify that, you get x squared plus 8x plus 78. And you discover they're equal. So we proved it by taking the left side and turning it into the right side. And if you take a look at this extra thing I've highlighted when we're actually going to be proving trig identities, that's what I'm referring to. When you're working on the left side, keep your eye on the right side because that's what you're trying to turn the left side into. Or if you're working on the right side, keep your eyes on the left side because that's what you're trying to turn the right side into. So the basic idea behind a proof is you want to take the left side and turn it into the right, or the right side and turn it into the left, and occasionally what we will discover has to happen is you need to work independently on both sides until they become the same thing. So you kind of meet in the middle somewhere. Now, in all of the examples that we're going to be dealing with, there is in your note package reference to a similar example in your textbook. Because some students really struggle with this, excuse me, my example 1 is similar to the example 1 in the textbook. So at the end of this lesson, if you don't understand one of these 4 examples, you can go try some of the other examples in your textbook. Sorry, I just had to unmute my mic for a second. So we are asked to determine the non-permissible values for that equation. Remember that non-permissible values happen because of division by 0. So when we find the non-permissible values here, we ask ourselves if there are any denominators in this. Now, I'm not working on the proof yet. I'm just saying first of all, that tangent of x is really sine of x over cos of x. I am not doing a proof here. I'm just saying, well, you know what? Inside of this equation somewhere, there is tangent of x, and inside of tangent of x, there's a denominator of cos of x. At the same time, I know something about what cosecant of x is, and what cosecant of x is the reciprocal of sine of x. So what I'm doing is identifying denominators so that I can see what is not allowed to be 0. This thing is not allowed to be 0. This thing is not allowed to be 0. And I want to pause there and see if anybody has any questions as to why cos of x is not allowed to be 0 and sine of x is not allowed to be 0. All right, there is one more thing that is not allowed to be 0 here. And I want you to take a look at the original equation and see if you can figure out what the third denominator is that's not allowed to be 0. It's a tough question I'm asking. The third thing is cosecant. And the reason cosecant is not allowed to be 0 is cosecant itself is a denominator of the entire expression. So the whole denominator is not allowed to be 0, and any denominators that are, I guess, hidden from view are not allowed to be 0. So now my question is, are we okay to that point? Does anybody have any questions on why? Well, let me go through them again. Cosine of x is not allowed to be 0 because if cosine of x were 0, then tangent would not be defined. Sine of x is not allowed to be 0 because if sine of x was 0, cosecant would not be defined. And cosecant is not allowed to be 0 because, get ready for this, if cosecant was 0, this whole thing is not defined because we would be dividing by 0. So those are the three non-equation statements, and then what you do is you go from that to a list of what x is not allowed to be. X is not allowed to be pi over 2 plus multiples of pi. I'm going to erase this. This was just kind of thinking about stuff. Why is cosine not allowed to be, or why is x not allowed to be pi over 2 plus multiples of pi? Because on the unit circle, when x is pi over 2 plus multiples of pi, we will be in those two locations where cosine is 0. Sine is not allowed to be 0. Where does sine equal 0? Here and here. So for those of you that were kind of using your calculator to avoid the unit circle, I think the time has come where you have to stop doing that. So x is not allowed to be 0 plus multiples of pi, and this never happens. Cosecant of an angle will never be 0 because it's 1 divided by something. But I include it anyway in our statement. You know what, I'm just going to say never happens rather than x never happens. I'm going to include this in the statement anyway because we do have to do that. So bottom line here is these four locations can be summarized by saying multiples of pi over 2. Those are the non-permissible values. Non-permissible values are probably more difficult for you to come up with than proofs. Any questions with the non-permissible values with this equation? It's all about denominators. Let's take a look at the first example then in terms of a proof. Well, actually, I guess we're verifying it first. Let's verify this. Let's use a graphing calculator to verify this. God, I don't want to start plugging in numbers. So it doesn't really matter what mode I'm in. I happen to be in radian mode. I am going to, for y1, and this gets tricky, I am going to enter the left-hand side of this equation. So I'm going to have tangent of x multiplied by cosine of x, and then I have to divide by cosecant, but as you know by now, we don't have a cosecant of theta or a cosecant function on our calculator. We have to go 1 over sine. But when you do that, you have to put that 1 over sine of x in brackets. The calculator needs to know that you're dividing by 1 over sine of x. You're not dividing by 1 and then dividing by sine of x, which is something different. And then on the right-hand side, it's 1 minus cosine squared of x, and we know by now that you enter cosine squared. It looks like cos of x squared, but it's not. You enter it that way. So tan cos over cosecant. And we have one of two things we can do. We can go to our table. Now my table has already been populated because it has a certain setting, but I can see that the left and the right side are always giving me the same numbers. I happen to be in radian mode, and those are degree numbers that I put in, but it doesn't matter. They could be radians, 88, 89, 90 radians. We could verify this graphically by choosing zoom trig, and it's going to graph the left side. Here comes the left side. That's kind of weird. And then once that's done, it's going to graph the right side. But since they're equal, you can't see that it's continuing to graph over the original graph. As I said to you before, if you want to see that in action, you can change one of these to a little bubble, bouncy ball, whatever you want to call it. By the way, the left side is the side that has the non-permissible values, so you will see the little bouncy ball, I guess not, it doesn't stutter in those places, but they are there. It's kind of stuttering. So that's the left side, and then when you watch the right side, it's going to trace over that and clean it up. Does anybody have any questions with B? All right, now the proof. The proof is the most important part of this. So what you have to do is rewrite the left side and the right side with a line down the middle. I'm just looking in my handout to see if I've done that for you, and I haven't. So take a second and rewrite the left side and the right side. There's no equal sign here. I know that you might think, oh man, that's being awfully picky. I know we know that they're equal, but you're asked to prove that they're equal, and you can't prove something is true by assuming it's true. So we're going to work on the left side and the right side. Now when I look at this, and I really hope, everybody is in agreement, the very first thing that pops in my head is the fact that the right-hand side is sine squared of x. I know that 1 minus cos squared is sine squared because of this identity on my formula sheet. Sine squared plus cos squared, sine squared of theta plus cos squared of theta is equal to 1. Okay, well if it's equal to 1 and I subtract cos squared from both sides, I get this statement. And we've talked about this a number of times. Sine squared of theta is 1 minus cos squared of theta. Okay, that's pretty basic then. But this is where we go back to what I taught you early last week, which is that you have to put a reason for what you did if it's an identity. So this is because of a Pythagorean identity. And this is a case where I told you with proofs you want to turn the left side into the right side or the right side into the left side, or meet them in the middle. because I hope what I'm about to say really makes sense when you listen clearly. There's no way I am going to, at this point, try to take sine squared and do something to it to turn it into tan x cos x over cosecant x. That just doesn't make sense in my mind. How are we going to take sine squared and turn it into something more complicated? What we want to do is take something complicated and turn it into sine squared. So let's rewrite everything in terms of sine and cosine. Tan is sine of x over cosine of x, multiplied by cosine of x. Now look at very clearly how I did this. And it's over cosecant, which is 1 over sine of x. So now we're at that stage where we have to write down the names of the types of identities that we used. And for the tan x, we used a quotient identity. And for the cosecant, we used reciprocal identity. Now we're at the stage where we can eliminate pesky denominators. How many of you see, though, that I don't have to multiply top and bottom by cosine x to clean this up? I can just multiply, sorry, that's a habit of mine. How many of you see? Type yes if you see why I don't need to worry about that cos x on the top. Right? It cancels. We could, and if you did multiply by an additional cosine of x, then you would just have more reduction to happen later. But if you take a look at what happened, this is a very simple proof, because these two cosines cancel. This sine cancels with that, with the other sine. So on the top, we are left with, well, what are we left with? We're left with this sine of x and this sine of x. We're left with sine squared of x. And we don't have anything except 1 on the bottom. So now we write sine squared of x. We're always working down. You're always working in this direction. You never work left to right. You have sine squared of x, and then you finish it by saying c. Let me move this a bit so I got a bit more room. I don't know why I have that so long. Then you finish it by saying c, the left side is equal to the right side. And that's what you actually write. You write left side equals right side. And you can abbreviate that even on a written response. We turn the left side, let me move this out of the way here. We turn the left side into sine squared of x on its own. We turn the right side into sine squared of x on its own, so they're equal to each other. Take a look at the work for that question. Does anybody have any questions about the first example or about any of the steps?
I have a question.
Go ahead.
So when we did on the left side, when you put your identities in,
Yep.
would you want to rewrite what you did and then do your work on the rewritten one, or can you just do all your work like you did if it was a written response?
Oh no, just exactly like I did.
Okay.
Yeah. Some people, for high school, what I did is good enough. Maybe in post-secondary, you might have a prof or a TA that says, oh, you got to rewrite it and you got to write down the specific identity. This is good enough, yeah. Any other questions with this example? All right, let's try number 2. And again, there's a similar example in your textbook. Now, the non-permissible values for this one, we are not going to do because you don't know how to determine non-permissible values for this. So we're not going to do the non-permissible values here. We're just going to jump right into the proof. So let's take a look at, why do I have nothing on the right-hand side? On the right-hand, well, I have tan of x. That's I guess I didn't write anything down for the right-hand side because the right-hand side is tan of x. I hope that you see, everybody, there's no reason for us to change tan of x. Could we write sine over cos? Yeah, we could, but that's tan. So we are going to be using identities to rewrite this. Now, sine of 2x, when you go to your formula sheet, and I would like you to do so, I don't want you to just be a passive student here today, especially today. Sine of 2x, when you go to your formula sheet, is equal to something. And whatever it's equal to, we are going to write it in the next step. So when we look at sine of 2x, I'm really hoping that most of you know what it is. Sine of 2x is 2 sine x cos x. I can't even see it. I guess it must be lower. Yeah, there it is. Sine of 2x is 2 sine x cos x. Again, I kind of hope that that's one of those ones that's stuck in your head now. You know it. So that's fine. I can rewrite sine of 2x as 2 sine x cos x. And then we have a problem. It's not a difficult problem, but it's something we have to address. We have to put in here cos of 2x. But cos of 2x is equal to 3 different things. So what we are asking ourselves, so there's my tan of x on the bottom. What we are asking ourselves is this, and this is my scrap paper / brain activity that's going on here. I have to ask myself, remember, cos of 2x is cos squared of x minus sine squared of x. I have to ask myself, if I do that, is it helpful? I have to ask myself, if I do this, and I decide to put in 1 minus 2 sine squared of x, which is also cos of 2x, is that helpful? And I have to ask myself if I do the following. And I realize that as I'm doing this, a lot of you already have the answer to where we're going here. Do I put in 2 cos squared of x minus 1? Because cos of 2x is equal to all 3 of those substitutions. Cos of 2x is cos squared of x minus sine squared of x. It's 1 minus 2 sine squared of x. It's 2 cos squared of x minus 1. So 1, 2, or 3, which is the wisest thing to do here? Which of these 3 substitutions is going to get me somewhere? And Katya's got it. It's number 3, because when you look at number 2, I'm going to rewrite these without the brackets. When you look at number 1, let's go with number 1, and you rewrite it without the brackets, you're going to have 2 sine x cos x, and then you have cos squared minus sine squared plus 1. And my question to you is, where would you go from there? You've got a trinomial on the bottom. Now, you could do something with it to eventually get there. Here, you're going to have on the bottom 2 minus 2 sine squared of x. But on the bottom, you're going to just get, on number 3, 2 cos squared of x. Because you have negative 1 plus 1, it's gone. So as Colton and Katya say, if you put in 2 cos squared of x minus 1, look what happens. You get, and we're basically done now. We're almost done. 2 cos squared of x minus 1. Put in double angle identities. So what do we get? We get 2 sine x cos x. And on the bottom we have 2 cos squared x, which I'm just going to choose to write as 2 cos x cos x. And I want to really highlight something here for you. So the negative 1 plus the 1 is 0. The reason why we are allowed to cancel, the 2's and to cancel a cosine is because everything along the top is being multiplied. If you had a plus or a minus anywhere in there, all bets are off. You can cancel this, you can cancel this, and we're left with sine of x over cos of x, which is tan of x. So we are left with this, which is tan of x. And then we can say left side equals right side. Have I done anything wrong here? Show you the big picture. I'll show you everything. The question is, would I get full marks on an exam? And the answer is no, I'm missing something. Exactly, Allison. I need to identify the identity I used, and I used quotient. If I were to actually do this question on an exam, if I were a student, I would have done this. Then I would have written tangent, because then it's a reminder, oh yeah, it's a quotient identity. You don't have to rewrite it. You could have left it the way it was, but you need to say you're using a quotient identity. Any questions with number 2? All right, let's take a look at number 3. So let's do the non-permissible values first. By the way, we're doing the non-permissible values because I'm asking you to. If you were given an exam question that just said prove, you wouldn't need to do the non-permissible values. This is just for extra practice. So cosine of x is not allowed to be 0. And you need to listen very carefully to what I'm about to go through here. Cosine of x is not allowed to be 0 because cosine of x is a denominator. Okay? And what I would do on an exam is say that since that is a denominator, cos is not allowed to be 0. However, there is a secant of x inside of this, which is 1 over cosine of x. And here's the part you need to listen carefully to. If you say cosine of x is not allowed to be 0 and all you do is point to this on an exam, but you don't make reference to secant and the fact that it has a cosine in a denominator, you would not get full marks. So what you would do is write out that secant of x is 1 over cosine of x, so this is not allowed to be 0, but we already have that covered. The other thing that's not allowed to be 0 is sine of x plus 1. That's not allowed to be 0 because sine of x plus 1 is a denominator. So these are our 2 statements about trigonometric functions of x and what they're not allowed to equal. They're not allowed to be 0. So where does cosine of x equal 0? Here and here. That's where cosine of x is equal to 0. Where is sine of x negative 1 at the bottom. So, again, something I want you to pay careful attention to. Had you not looked at the sine of x plus 1, you would have still got these two locations as being non-permissible. But even though sine of x plus 1 not equal to 0 is one of those, you wouldn't get full marks unless you addressed it. So our non-permissible values could be written as pi over 2 plus multiples of pi. And I think the last time we talked about non-permissible values, I did forget to say that n is an integer. So this is the thought process that would go on to give us our non-permissible values. Any questions with the NPVs for example 3? All right, let's do the actual proof now. And I will warn you right now that there is a very special thing we need to learn from this example. And we'll get to it, but all of those tips I've given you do not include this one thing. There is absolutely nothing that you can do with this. There's nothing you can do with it. So what we're going to do is work on the right-hand side. Now I'm going to write everything in terms of sine and cosine. And if I do that, I'm going to have 1 over cosine of x minus sine of x times 1 over cosine of x. And notice how kind of slow and deliberate I'm being in how I write this. Everything is lined up neatly. I've got things that are numerators like 1 and sine of x and 1. Things that are denominators like cos of x and 1 and cos of x. And then on the bottom I have cosine of x. I need to address the identities that I used, which would be, well, I only used one. It's a reciprocal identity. And now what I'm going to do, and here's, by the way, here's poor planning on my part. You see where I wrote reciprocal identity? I want to be able to leave room to write that I have to multiply top and bottom by cosine of x. So this was a little bit of bad planning on my part, and if I were writing an exam, I would erase this and move it over. Now I can just move it over, but don't crowd things in. If you have to rewrite something, then by all means rewrite it. So I'm going to multiply top and bottom by cos of x to eliminate these pesky denominators. So on the top I have my 1 over cos of x minus my sine of x over 1, and it's being multiplied by, each of these are being multiplied by cos of x. And this is over the cos of x, which was on the bottom, multiplied by the cos of x, which I'm multiplying the bottom by. So you may have to, take a close look at what I have written in the pink step and ask yourself how you get to this step. All I did was I took this cosine of x and I multiplied it through. That's all I did there. And by the way, you might wonder, why did I only multiply the cos of x by this whole thing and not by both? Because there's multiplication in there. So what happens? On the top, I end up with, just a second here. I just got to check my work here. Secant is 1 over cos, multiplied by cos, I get 1. Does anybody see what I forgot to write here? There's something that I just missed in going from one step to the next. And it rolled off my tongue as I wrote it so well that I think you guys got sucked in. There's a cos x here. And therein lie the perils of doing this. If you miss some little thing, then you're going to make a mistake. So any questions in going from the pink one to the one with the green dot? All right. So now what we have is, let's see what cancels. I have 1, the cos x cancels with the cos x cancels with the cos x. So I am left with 1 minus sine x over cos squared of x. So this is equal to, on the left-hand side, I'm just rewriting the left-hand side so you can see it. It better be equal to 1 over 1 plus sine of x, and it is. Or sine x plus 1, doesn't matter. And I really am curious here. Does anybody know what we should do here? We haven't done anything wrong, okay? That's the first thing that you need is some reassurance. We're on the right track. But what we've run into is a very dark, dark place in our journey. And we just have to figure out how to get past it. Those two things, believe it or not, are equal. Does anybody have any ideas? Do you mean 1 minus sine x? Is that what you actually mean? Is cos x 1 minus sine x? I think I know what you mean, Aiden, but cosine of x is not 1 minus sine x. Okay, we can't do that. I know that you may feel as though cosine of x is 1 minus sine of x, but it's not. Cosine squared of x is 1 minus sine squared of x. But we're on the right track. So I'm going to just shelve this for a second. And you don't need to write this down. You just need to open up your mind, relax, take a breath, and follow what I'm saying. I gave you the responsibility a number of days ago of remembering this. Even though it's on your formula sheet, you should know that. And then I said, you know what else you should remember? You should also remember this. I'm just going to rewrite it a little smaller. You should also remember that cos squared of x is 1 minus sine squared of x. And you should also remember sine squared of x is 1 minus cos squared of x. Remember me telling you now you have more things to remember because that identity has at least 3 different forms? Well, there's another form it has. Cos squared of x is 1 plus sine of x times 1 minus sine of x. Because this is a difference of squares. If I asked you to factor 1 minus r squared, you would write 1 plus r, 1 minus r. Well, that means 1 minus sine squared is 1 plus sine, 1 minus sine. So now you need to be aware that cos squared is 1 plus sine, 1 minus sine. And sine squared is equal to 1 minus cos squared, which means it's equal to 1 plus cos x, 1 minus cos x. Now, how is this helpful? Well, normally, everybody, you take something like 1 minus sine squared and you write it as cos squared. We're going to do the opposite. We are going to write you guys seeing those lines? Blue lines?
Yeah.
Can't tell you what's going on there. We'll just have to bear with it. What we're going to do now is rewrite this as 1 minus sine x over 1 minus sine squared x. We're using the Pythagorean I don't know what that is. We're using the Pythagorean identity. And what that allows us to do is factor the bottom of this. The bottom of this is factored as a difference of squares. And I'm curious, how many of you, by typing yes, see that as soon as we factor it, we'll have our answer. We will have it equal to the left side. Right? You're going to have something that cancels right away. We have 1 minus sine x on the top. And then on the bottom, this factors to 1 plus sine x. 1 minus sine x. Well, the 1 minus sine x is in brackets on the top. The 1 minus sine x is in brackets on the bottom. So we're left with 1 over 1 plus sine x, which is, I'll just scroll up, which is what we had. So now you can say left side equals right side. You will recognize the need to play around with this difference of squares when you see one side of your identity that you're trying to prove that has, say, 1 minus sine x, and on the other side there's a 1 plus sine x. By the way, 1 plus sine x and sine x plus 1 are the same. So there is all of our work for that question. Any questions with example 3? All right, let's take a look at example 4. And let's, I don't know, do we want to do non-permissible values again? I guess we should. So when you look at this equation for non-permissible values, there are no reciprocal identities and there are no tangents. So we don't have to worry, in other words, everybody, we don't have to worry about hidden non-permissible values. We simply have to say that 4 sine squared of x minus 1 is not equal to 0, and 2 sine x plus 1 is not equal to 0. And we have to solve both of these, and you've already been taught how to solve these. If I rearrange the equation on the right, I get sine of x is not equal to negative 1 over 2. This equation on the left, everybody, has a quadratic term and a constant term, but no linear term. So we can just go ahead and start rearranging and getting sine squared of x equals 1 over 4. I add 1 to both sides and divide by 4. And then I take the square root. And this is not equal to 1/2. And when I take the square root, of course, the sine squared turns into sine. Any questions with what I've written there? Are you happy with that? I'll ask a different question then. What have I done wrong? What would I lose marks for on an exam? We are getting there, Aiden. We're not done. Yes, you're right. Actually, I want to address that. What some people do is they just end it there. But I want non-permissible values of x, so we still have to find the unit circle values. But I've still done something, even before I do that, there's something that I've done incorrectly. And even though I will get the right answers, there's something I'm missing. And it's that when I take the square root, it's plus or minus. I know that we already have sine of x equals -1/2 accounted for on the right-hand equation. But that doesn't mean we can ignore the left-hand equation. What we do is we say, now we're left with these two equations. Sine of x cannot be equal to 1/2. Sine of x cannot be equal to -1/2. And on the other denominator, we had sine of x is not equal to -1/2. And then you can say, well, we've already got this one covered. We don't need to do it twice. So now, as Aiden said, we have to go to the unit circle. Where is sine equal to positive 1/2? Well, here's 1/2, so here and here. Where is sine of x equal to -1/2? Here's -1/2 for sine, so here and here, which means we have this rotation angle and this rotation angle, and it's going to get messy, this rotation angle and this rotation angle. Sometimes it's better to draw them separately. I drew them all 4 on 1. So pi over 6 5 pi over 6, 7 pi over 6, and 11 pi over 6. And if you want a general statement, you would say pi over 6 plus multiples of pi, and 5 pi over 6 plus multiples of pi. See, the first statement, pi over 6 plus multiples of pi, will cover this and this. The second statement will cover the other two. By the way, everybody, I wouldn't get really hung up on non-permissible values. I mean, we do our best with them. It doesn't form a big part of any kind of evaluation or exams. Let's move on and do the proof. And this proof, everybody, this proof looks monstrous. It looks like the kind of thing where I get that a student would turn the page on an exam and see this and just melt. But it turns out it's not tough at all if you know the steps to follow. So write everything in terms of sine and cosine. Well, there's really only one thing we can do here, and it's to rewrite that sine of 2x on the top of the left as 2 sine x cos x minus cos x. So this part here got rewritten to 2 sine x cos x. This is over 4 sine squared x minus 1. And there is only one thing you can do on either side right now. Look over your list of tips and tricks for working with and proving identities. What is it we can do? What's the only thing we can do? Is my mic still on? Yep. I wasn't trying to make a joke. I was being serious. So what can we do? Factor, exactly. It's the only thing you can do. I'm just going to pick on the left-hand side because I'm sitting in my chair and that's where I happen to be right now. It's right in front of it. So I have a common factor on the top. I have a common factor of cosine of x. I can factor out cosine of x out of the top and be left with 2 sine x minus 1. Now, once you've written that part down, answering yes in the chat to this question if you agree. Are you now, you personally, starting to see where this might go? And that's fine. A couple are saying yes. It takes a little while to process it and a little while for the, all the electrons to go through all the wires and get beamed into space and back. What can we do to the bottom of the left-hand side? Oh, the answer is factor, but what I mean is, how can we factor the bottom of the left-hand side? Difference of squares, exactly. Is 4 sine squared of x a perfect square? You bet. It's a perfect square of 2 sine x. Plus and minus. Is 1 a perfect square? Well, yeah. It's one of the simplest perfect squares, if not the simplest perfect square out there. Oh man, look at that. Look at that. I know I get more excited about these things than you do, but look what it simplifies to. Cos of x over 2 sine x plus 1. I should move that over here. The 2 sine x minus 1's cancel. I am really curious, and I'm going to give you almost a full minute to think about this. How many of you can see that this on the right-hand side, how many of you can see that this on the right-hand side is in fact equal to cos x over 2 sine x plus 1? One person. See, the way I ask that question might be a bad way for me to ask it. I'm not saying that I want you to just stare at it. I want you to stare at it and ask yourself what you would do to it and what would happen if you did that thing to it. Kathy already said we got a factor. So can you factor something out of the top? Well, let's find out. There's a common factor of cosine of x here on the top. Right, I have this term plus this term, and there's a cos x in each term. So why don't I factor that cosine of x out, and what am I left with? Out of the first term, sine squared of x plus, out of the second, cos squared of x. How many of you now see that the right-hand side is in fact equal to the left-hand side? And why? And Aaron, you raised your hand. Do you have a question?
Sorry, that was an accident. I was typing.
Okay. So, yeah, that sine squared plus cos squared is equal to 1. This is, the most famous identity. So what we're left with is cosine of x over 2 sine x plus 1. And you can say left side equals right side. And if you're like me, and when I was in high school, I already told you this story, this kind of ticks me off as a high school student. We would not get full marks here. Even though you've got good algebra skills, you know exactly what's going on. We need to write down the names of the identities we used. Double angle identity. When we replaced, what did we replace? When we replaced sine of 2x with 2 cos x sine x, we used the double angle identity. And then to go from here to here, we use the Pythagorean identity. And that's it. I like this example because it looks brutal. Like when you first look at it, like what do you do? But look at the amount of work we did in this example. And compare it to the amount of work we did in, say, example 3. Example 3, if I can find it, is a lot more work. There's a lot more going on. Perhaps even example 2. I can't remember. This is example 2, I believe. Example 2, I think, has a lot more going on because there's more identities involved. Example 4 is basically factoring. So in your textbook on page 314, it's questions 1 to 8, 10 to 13, 17 and 18. I believe, but can you confirm for me that in the next page of your handout there is a sheet of identities as well? Okay, so if you do need extra practice, there's that. We're almost done chapter 6, so there's other proofs in that chapter review section you could look at doing. There's one more topic we're going to cover tomorrow though. So you got lots of time. You got 45 minutes here today to practice with proofs. Again, class is here officially till 2:30, but I will be here until 3.